Ooh, significant figures. Oh, our sig figs. Okay.
Yeah, significant figures like President Obama.
Yep.
Okay.
Or me in my classroom. I'm significant.
Yeah, you are significant. It helps. Significant figures basically are a mathematical tool that help us to define the precision of our measures and our calculations.
Okay.
That way, when we're scientists and we write a paper and we get it published, we don't have to say, we measured this using a metric ruler that had tenths of centimeters. As long as we follow the significant figures rules for measuring, then everybody in the world understands how we arrived at our measurements.
Okay.
If we used a caliper, we could go for more digits beyond those 2 digits past the decimal.
Okay.
All right. The last significant digit in any number is always the one we are least certain of.
So it was the last one in red that we just did on those examples.
Basically, we were calling that the guess digit. It's the last one that we're. It's the one that we're least certain of.
Okay.
Every other one we're pretty certain of.
Okay.
All right. So, for example, if we have a measurement of 10.00 grams, that means that we've used a fairly expensive balance first off, because look at this, we have a tenths and a hundredths place here. So what that tells me is that the balance indicates that we have precision to the tenths place.
And the tenths place is that zero there.
The balance was sure to this point, and we had to guess that. So it could have been 10.01, it could have been 10.
Oh, sometimes, sometimes our balances flitter between 2 numbers.
Right. No, that's why it flitters, is because that last digit, the electron balance is just guessing.
Okay.
Okay. Just the same way we would if it was an analog instrument. Okay.
Okay.
All right.
Yeah.
All right. So 10.0 grams tells me something a little bit different. 10.0 grams tells me that this place value was my guess.
Okay.
Okay, so that's the tenths place value. So this balance actually costs less money, probably.
Yeah, because it's not as precise as the first one.
It's definitely not as
it only
precise.
goes to the ones place, yeah?
It indicates precision to the ones place. So we are sure at this place value here.
Okay.
All right. It means the instrument had its smallest markings in the ones place value.
All right.
All right. Finally, 10 point grams indicates something completely different. All right. It's indicating precision to the tens place, so we're sure of this number, and the 0 is our guess.
Okay.
Okay. Notice the decimal points with significant figures is going to be an important thing, whether you write it or not.
All right.
I think we're about to get into that.
Okay. Recognizing sig figs.
Yeah.
All right. Recognizing significant digits or significant figures. All non-zero numbers are significant. Zeros between non-zeros are significant. So sandwiched zeros are significant. Zeros in front of non-zeros are not significant. So if they're placeholders, they are not going to be significant. Trailing zeros are only significant if a decimal is involved. If they are merely placeholders, they are not significant. If there's a decimal, they're going to be significant.
So it's not a matter of they're important or not, Mrs. G?
Nope, just a matter of whether they're part of the significant measurement.
So significant figures is a new definition. It's a new vocabulary term I've got to be able to use.
Yes.
Okay.
It basically tells you how good an instrument is you are using to mass or read a volume or measure a length of.
Okay. All right. That sounds good. I think I understand that. Ooh, there's a special case.
Oh, I love special cases.
There's always a special exceptions to the rule.
Exceptions to the rules.
All right. Exact values have an unlimited number of significant digits. So, for example, exact values include counts.
Oh, counted numbers.
So, like, you know, the count.
Okay.
1, ha, ha, ha. 2, ha, ha, ha. So, you can count there's 12 eggs in a carton. You're not really going to measure that because there's not really a measuring device that measures 12 eggs in a carton. You look at it and you count 12 eggs.
You wouldn't have a ruler out.
The number of students in a class, I don't really have a measuring tool.
Okay.
There's not a meter stick or anything that measures how many students are in my class. I just count it. The number of hydrogen atoms in H2O, so there's 2. So that's a count also.
Okay.
So count values don't have any sig figs.
Got it. Okay.
All right. And the other one is?
Conversion factors. When we start converting and using a ratio of 1 kilometer to 1,000 meters, that will not have a bearing on our significant figures.
I think you mentioned this one earlier in one of our earlier lectures. a kilo, by definition, means 1,000. So this says 1,000 meters, and that's the same as 1,000 meters. It's just a conversion factor. It's a definition.
Okay.
All right. When doing math operations, it's important to ignore those values that have unlimited numbers of sig figs.
Okay.
All right, so we'll try these right now, just to point out how many sig figs. My rules go pretty simple. Non-zero numbers.
And a zero sandwiched between.
And then a zero sandwich. Man, I'm hungry now. Sandwiches. Sorry. All right, and notice this is a measurement, so I can actually answer 3.
And all measurements have a unit, don't they, Mr. Kane?
Yeah, and if my units indicated something that was counted, how many sig figs would this have been?
Unlimited.
If this had actually said, instead of centimeters, if it had said you can't have 40.7 dogs, can you? Pencils. How about pencils? That's less gross. So if you had 40.7 pencils, you counted up 40 and then 7 cents of a pencil.
Yep. You broke one in half, or broke one in 7s.
That is actually going to be unlimited.
It's a counted number.
Mrs. G, could I just write an 8 on its side?
Yep, infinity.
Infinity. It's got an infinite number of sig figs. All right. This one here, if I do this number, non-zero numbers, I've got 4. Zeros sandwiched. Well, I've got no zeros sandwiched.
Right.
Zeros in front, I think the rule says never.
Never.
So none of these are significant.
They're placeholders.
And a placeholder, so that's it, 4.
Okay.
All right. This one, we've got those
2 non-zeros, okay, and a zero sandwiched in between, and a placeholder.
And placeholders, so no,
3.
Those aren't significant. 3. All right. So this one here, we got non-zeros.
Now, one of those rules said when there's a decimal and there are zeros to the right of the decimal, they're significant. So those 2 zeros have to be significant, right?
Now,
does
it matter if they're to the right of the decimal or left of the decimal?
Well, if they're to the left of the decimal, they'd be in front of non-zeros, like the one above it.
Well, here, let's do this. Let's do this first. Let's finish this.
Okay.
So you were saying.
Well, if they're to the right of the decimal, those are the other rules. If there are zeros to the right of the decimal, they're significant. So those 2 zeros have to be significant.
Right.
So there's got to be 4 of them.
So 4 of them.
Significant digits.
Now, Mrs. G, what if it looks like this? What if I have 5,800 grams written like that?
Oh, I see what you're saying. Yes. Then there's 4 because you've got the decimal is kind of like a significant entity. And if there's a decimal and something between 2 significants, then it's significant too, right?
Okay, right.
So if the 8's significant and the decimal's significant, so are the zeros.
All right, so that's 4 also.
That is.
Final one here.
Oh, first off, there are no units on that measurement.
Oh, hold on. Let's fix it. Grams. Okay, now it's a measurement.
Okay, now I'm happy.
All right.
There's no decimal.
No decimal. So I can count my 2, but I can't count any of the zeros because
those are trailing zeros.
They're trailing, but there's no decimal.
No decimal, so
it's
they are
just 1.
insignificant. All right.
Okay.
1. Ooh, scientific notation.
Sci Not.
Yep, Sci Not. Used to communicate large and small numbers. For instance.
That's a small number.
So let's see. On the left, you have 0.00000000100, and then you turn it into 1.00 times 10 to the negative 9.
Well, let's see. It went 3, 6, 9 decimal points.
So if you're moving the decimal to the right to write a scientific notation, it's going to be a negative value.
Right. And what is that negative
exponent?
That negative exponent is actually just telling us that the number is small, right?
Right. That means it's a small number.
Small number. So, and that looks true. This looks pretty small to me.
Yeah. I don't have a balance that could read that far out to the right.
No, neither do I. Mrs. G, why is there a space after 3 digits and a space here after 3 digits?
I think it's just so you can easily count it by 3s.
Oh, okay. Kind of like a comma.
Yes, kind of like a comma.
I guess you can't put commas after a decimal, can you?
No.
It's not accepted. This number here.
My salary.
Oh, yeah. Where's the decimal?
Yeah.
Over here for our salary. No. Where is the decimal?
Well, as written like that, the decimal is after that last zero here, the original decimal.
1,300,000,000. Yeah, I
Yeah.
guess the decimal is assumed to be
Be
here.
right there,
right?
yeah, it's understood
But-
to be right there.
But they didn't write it there on purpose because
Right.
they wanted to indicate that only those two digits were significant.
yeah.
Right? Because if they put a decimal,
Then they're all
then
significant.
they're all significant, all those zeros.
So you'd have to write them all out if you did your scientific notation.
But if the decimal was there and I was trying to move it to figure out how to write it in scientific notation, 3, 6, and 9. All right. So the rules for scientific notation are that you have one non-zero digit in front of the decimal, and that any other digits that you have that are significant are also written,
Okay.
and then you have times 10 to a power that indicates how many places the decimal got moved.
All right, so if the decimal's moving left, it's a big number. If the decimal's moving right, it's a small number.
Right.
Okay.
And a big number is represented by a positive exponent, a small number by a negative exponent.
Okay.
All right.
All numbers before the exponent are significant.
Yeah.
Okay,
Sounds
so
easy enough.
the example on the left has 3 sig figs, and the example on the right has only 2.
Yeah, that's what it looks like because
Okay.
we got 1.00, so those zeros are significant because the
Okay.
decimal's there. And 1.3, which is 2 sig figs.
Okay.
So 2 here and 3 sig figs there.
All right.
Rewrite these in scientific notation.
Okay, let's see. 9.3, and it's a big number. I'm moving the decimal to the left, so big number. 9.3 times 10 to the 7.
That's, yeah, okay. 6,
Right? 1, 2,
3,
4, 5,
6,
6,
7. Yeah, 9.3 times 10 to the 7th.
Can count.
All right.
Ooh, that's a small number.
We're going to move it twice to the right, right?
Yeah, so I'm moving it to the right, 1.0.
Is that 0 significant?
Yes, because it's a trailing 0 after a decimal.
Yeah, so it is significant, so I'm
Yes.
going to put a 0. 1.0 times
10 to the negative 1, 2.
Yeah, I moved it twice, so negative
Okay.
2.
Okay, so no decimal, and as written, there are 2 sig figs, so my scientific notation should also have 2 sig figs, correct?
Correct. So when I put my decimal in here, it's not actually there for sig fig purposes.
Right.
What did you get?
1.7 times 10 to the 3rd.
It looks good.
All right.
Ooh.
All right, so we're moving the decimal right, so my exponent's going to be a negative value, correct?
Yep, I think so.
2.546 times 10 to the negative 4.
Yeah, we moved it 3 places and then
And
one
another
more,
one.
which is 4, negative 4.
Now, how come we can't just get away with 2.5 times 10 to the negative 4 on that one, Mr. Kane?
Well, you don't want to round these.
Okay.
The number was written this way, supposedly, because it was indicating how many sig figs it was. And so you want to indicate the same number of sig figs in your scientific
Since
notation.
there are 4 sig figs in the long way, there got to be 4
There's
sig
gotta be
figs
4
in the
sig
Sci
figs.
Not way.
Yeah.
Okay.
Mm-hmm.
Got it.
4 is 4, same thing. The one thing that all of these things are missing,
Something that would be marked wrong, Mr. Kane, if
Yep.
I was grading this test or quiz.
yeah, it would all be, these are all unitless.
Yes.
So we need units on these. This is an assignment. Go ahead and try this.
All right, on a sheet of paper.
5 of
1,
them.
2, 3, 4, 5. Put your name on the sheet of paper. Number it 1, 2, 3, 4, 5. Write the number down in scientific notation and then in standard form and turn it in the next day.
Want to see both of them?